Welcome to the concept of an autonomic avionics platform and the resulting software engineering challenges. My name is Björn Anikofer. I'm from the Institute of Aircraft Systems of the University of Stuttgart in Germany. In the background image, you see an avionics bay on board of an aircraft. There are many computers responsible for your safety and comfort on board, and we would like to introduce self-organizing and self-configuring systems into that. So what we have today is the concept of integrated modular avionics, which is a standardized resource-sharing distributed computing system as depicted in this little sketch here. We have a standardized operating system, which can take several software partitions in parallel, and approximately 100 safety-critical systems with 10 times more functions are hosted there. Those modules are all standardized, which means they need to be put in operation with configuration parameters. There are millions of that in total, and they are currently mainly developed manually, which creates a huge effort at the aircraft integrator. So what we would like to have is not so much different. We just replace the original pictures here with white boxes. Those are modules of a so-called plug-and-fly avionics platform, which shall behave self-configuring, self-optimizing, self-healing. First of all, it shall detect the topology itself, so no need for configuration, and this is managed in a platform-wide consciousness. Then the system is addressed by a model-based system specification, so no source code and binaries, but a model with additional constraints on safety, performance, which are managed by the platform. You don't have to specify your redundancy. The redundancy is automatically created from your safety constraints, and also redundancy management blocks are introduced, and the platform decides itself based on the performance of each module and the available resources and performance constraints where to allocate each function. By doing so, the number of configuration parameters you have to create manually reduces to 0, and if you do that continuously, you automatically get something called dynamic reconfiguration, which means that if the function or the hardware changes, you can think if there is a better solution, and in this case just move to functions and dynamically update also your consciousness. So technically this should be feasible. However, we also have the certification and safety in aerospace. So first of all, we have regulations. There are for each aircraft type different regulations, but basically they define an acceptable risk for your system functions. Then you have accepted means of compliance, which put some numbers and process instructions and also test coverage instructions to your development. And if I just summarize that very quickly here, certification for the avionics system today means that every state of your avionics system, including the faulty ones, is precisely known at the stage of development and tested and documented. So there is actually no room for dynamic configuration. So if you suggest that to your aircraft certification authority, you might get this gesture here. So how can we approach that? So we would like to have dynamic configuration. Our starting point is that we have built a physical topology from existing PAFA modules and try to put a function or several function specifications. In addition, we assume that we have within those function specification pre-qualified blocks, which are just developed the traditional way from source code by requirements and testing. They are ensured to be correct. And we have that for the function itself and also for the system and redundancy management part. So first step for the system would be to detect its topology. Then decide based on the requirements of the function how many redundancies and how many redundancy mechanisms I need. Then we need to allocate that based on the available resources. Then comes something new. We must ensure safety, so we have to recalculate if all the safety constraints are met. Then test the function itself, so there must be some functional specification, what shall be the result of each function. And then finally a releaser, which decides if I can fly or no. So if I cannot fly, this is not really a problem. If it happens in the first stage, I just will not take off. If it happens during dynamic reconfiguration, you see here I still have my traditional redundancy available, so there will be no direct fault if there is a no-go decision. So why did I draw this as a circle? You might already see that this is something you know very well. It's the MAP-K cycle with monitor, analyze, plan, execute, and knowledge. And there's something new in green, which I shortly introduce. So that's my MAP-K cycle. And the new element we see here is the qualify action, which shall mimic the activity that usually the humans at the qualification agency will carry out. And this is something we name here as a MAP-QEK cycle. And the second addition we need is this MAP-QEK cycle needs also to be redundant. So we need several instances of that that have to form a consensus. So lastly, I would like to show the actual technical concept. If we look inside of such a plug-and-fly module, there we would like to reuse something that is well established in this integrated modular avionics architecture, and that is a partitioning operating system according to the ARINC 653 standard. Partitioning means that different software parts of different criticality can run side by side and have no unintended way to influence each other. And therefore, we would like to propose 4 partitions. I start on the right-hand side where we have the live execution unit, which is responsible for executing a schedule of system function blocks and routing the system signals accordingly. On the left-hand side, we have our planning intelligence, which does all the complex parts, topology discovery, redundancy generation, and function scheduling. All this information is stored in a consciousness, which is then copied into a virtual qualification authority that mimics the qualify part of the MAP-QEK cycle and does the security and safety assessment, requirements test, and releaser. For requirements-based testing, we just have a second execution unit, which is just a copy of the live execution unit, but which can be fed with the new plan in advance and then see if that plan behaves correctly. For sure, we must make sure here that no real environmental things are influenced, like sensors and actuators. There must not be a real output here. So if we are sure on the plan, we can just swap between those 2 partitions. The verification execution unit becomes the live execution unit and vice versa. So the partitioning enables us some benefits in the software development. This is qualified in design assurance levels in aerospace. For the executional part and the operating system itself, we need the highest design assurance level, which is DAL A, which means the highest effort and test coverage. However, by separating this planning intelligence, which maybe has the most complex algorithms, we can assume here a very low DAL level because it doesn't execute anything. It just makes a plan, and if that plan is correct and fulfills all the requirements from the regulations, must to be made sure within the virtual qualification authority. And that's maybe the hardest challenge in this concept here. So besides that, we see several other challenges. First, the consciousness model, which is a complex hierarchical information storage. We propose to use a domain-specific model here. However, if we do so, we need a qualified runtime environment for domain-specific models, which is currently not available to our knowledge. Then we have the qualify part. Here we must make sure that all the algorithms we use for qualification are deterministic and provable. And also we must convince the certification authority that our way in mimic their activities online is appropriate. And last, a smaller challenge is forming a consensus on such complex data where traditional algorithms may lead to infeasible bandwidth and computing resources. So the way forward is that we have a project that is developing the plug-and-fly avionics. In the next 3 years, we would like to show the technical feasibility. And we also have the European Certification Authority on board to show a way how certification could work. At the end, we will not go into fly, but you see here we will have a lab demonstrator of an air taxi, which probably runs then using dynamic configuration. Then we have a more industrial project where we develop a certifiable runtime for domain-specific models and implement that in a programming language that is liked by certification authorities. And last, we already created a prototype for the consciousness model which is already open source and will be developed and evolved within the next years. Okay, thank you very much for your patience.